Hello all. So today we are talking about chapter 6 and about protein, the tissue builder. So protein is one of our most essential nutrients for optimal health. Additionally, it has a wide variety of physiological functions that are essential to optimal physical performance. For example, protein forms the structural basis of muscle tissue, is the major component of most enzymes in the muscle, and can serve as a source of energy during exercise. Because protein is so important to the development and function of muscle tissue, and because protein is so important to the development and function of muscle tissue, and because most feats of human physical performance involve strenuous muscular activity in one form or another, it is no wonder that protein has persisted throughout the years as the food of the athlete. Indeed, surveys have revealed that many high school and college athletes believe that athletic performance is improved by a high protein diet. Protein is one of the best-selling sports supplements. A best-selling diet book suggests that protein is the key macronutrient for the athlete and for health as well. Companies that market nutritional supplements for athletes have capitalized on this belief. Probably the athletic groups most susceptible to the lure of protein supplements are bodybuilders and strength-type athletes such as weightlifters and football players. Numerous high-protein products have been developed for these athletes in attempts to exploit the protein-muscle strength relationship. In recent years, specific amino acids have been theorized to maximize muscle mass and strength gains and have been advertised extensively on the internet and in magazines for bodybuilders. Some advertisements even suggest that certain amino acid mixtures have an effect similar to drugs such as anabolic steroids, which have been used to stimulate muscle development. Protein supplements are marketed for other types of athletes as well. Although protein is not regarded as a major energy source during exercise, research has suggested that endurance athletes must use some specific amino acids for energy production under certain conditions. Protein supplements, often combined with carbohydrate, are marketed in sports drinks to endurance athletes. Additionally, specific amino acids have been theorized to delay the onset of fatigue during prolonged exercise through the effect on neurotransmitters in the brain. There is no doubt that an adequate amount of dietary protein and related essential amino acids is required by all individuals. However, the advertisements directed toward athletes imply that additional protein, usually in the form of protein or amino acid supplements, is necessary for optimal performance. Although the National Academy of Sciences has indicated that the recommended daily allowance, RDA, provides sufficient protein to athletes, some investigators recommend that athletes in training increase their protein intake. However, these investigators usually recommend that the protein be derived from natural food sources, and the amount of protein recommended is well within the acceptable macronutrient dietary range. Other dietary supplements related to protein or amino acids, such as amines or various metabolic byproducts, have become increasingly popular in recent years. One of the current hot sellers is creatine, but other supplements such as inosine and HMB are also available. In most cases, these dietary supplements have been marketed to strength-trained athletes as a means to foster muscle growth and strength development, but some are intended for use by athletes involved in other sports such as aerobic endurance events. Does the physically active individual need more protein or related dietary supplements in the diet? The information presented in this chapter should provide a general answer to this question. Topics to be covered include dietary needs and sources of protein, metabolic fates and functions in the body, the effects of protein or exercise on protein metabolism, and dietary requirements. The ergogenic potential of protein, amino acids, or other related supplements and the health aspects of dietary protein. So, what is protein? Protein is complex chemical structure containing carbon, hydrogen, and oxygen, just as carbohydrates and fats do. Protein has one other essential element, nitrogen, which constitutes about 16% of most dietary protein. These four elements are combined into a number of different structures called amino acids, each one possessing an amino group and an acid group, with the remainder being different combinations of carbon, hydrogen, oxygen, and in some cases sulfur. There are 20 amino acids, all of which can be combined in a variety of ways to form the proteins necessary for the structure and functions of the human body. The protein is one of our most important essential nutrients. It provides structure for body tissues, formation of enzymes, may provide energy, and when used in sports can be, of course, needed for strength and endurance athletes. And as far as the implications for health, the good proteins and the Omni Heart Diet that we'll talk about and that we have talked about will be discussed a little later. So the chemical structure of alanine, an amino acid, the amino group contains nitrogen, while the acid group is represented by COOH. The body may also modify the structure of dietary amino acids, such as converting proline to hydroxyproline to meet its needs. Figure 6.1 depicts the formula of the alanine, an amino acid we will talk about later. And here you see proteins are created when two amino acids link and form a peptide bond. Hence, a dipeptide is formed. As more amino acids are added, a polypeptide is formed. Most proteins are polypeptides, combining up to 300 amino acids. And you can see here it's the building of a protein. Now, protein is contained in both animal and plant products. Humans obtain their supply of amino acids from these two general sources. So is there a difference between animal and plant protein? To answer this question, let us first look at a basic difference between two groups of amino acids. Humans can synthesize some amino acids in their bodies, but cannot synthesize others. The 9 amino acids that cannot be manufactured in the body are called essential or indispensable amino acids and must be supplied in the diet. Those that may be formed in the body are called non-essential or dispensable amino acids. 6 of the dispensable amino acids are conditionally indispensable, which means that they must be obtained through the diet when endogenous synthesis cannot meet metabolic demands, such as in severe catabolic or breakdown states. Although nutrition scientists prefer the terms indispensable and dispensable, this text uses the terms essential and non-essential because they are the most commonly used. So it should be noted that all 20 amino acids are necessary for protein synthesis in the body and must be present simultaneously for optimal maintenance of body growth and function. The use of the terms essential and indispensable in relation to the amino acids is to distinguish that they must be obtained in the diet. And here in Table 6.1, it presents the dietary essential, non-essential, and conditional essential amino acids. The proteins ingested as animal products are generally regarded to be of a high quality than those found in plants. This is not to say that an amino acid found in a plant is inferior to the same amino acid found in an animal. They are the same. When we look at the distribution of all the amino acids in the two food sources, however, we can see the two major reasons animal protein is called a high quality protein, whereas plant protein is of a lower quality. The PDCAAs for egg white and meat is respectively 1.0 and 0.92, while the score for kidney beans and whole wheat is respectively 0.68 and 0.40. Animal protein is a complete protein because it contains essential amino acids in the proper proportion to human requirements. As noted, all 20 amino acids must be present simultaneously for the body to synthesize them into necessary body proteins. If one amino acid is in short supply, protein construction may be blocked. Having the proper amount of amino protein in the diet is a good way to ensure receipt of a balanced supply of amino acids. Some protein supplements marketed to athletes are made from animal product, including milk, egg, and whey protein. The National Academy of Sciences indicates that different dietary sources of protein vary widely in their composition and nutritional value. The quality of a source of protein is an expression of its ability to provide the nitrogen and amino acid requirements for growth, maintenance, and repair. The key factors are digestibility and the ability to provide the indispensable amino acids. All natural, unprocessed animal and plant foods contain all 20 amino acids. However, the amount of each amino acid in specific foods varies. Over the years, a number of different techniques have been used, usually with animals, to assess the quality of protein in selected foods. One of the most widely used is the Protein Digestibility Corrected Amino Acid Score, the PDCAAs, which incorporates real-life variables, including the amino acid content and digestibility of the protein. Scores can range from 1.0 to 0, with 1.0 being the highest quality. We need to not go into detailed discussion of all techniques to evaluate protein quality, but essentially they focus on the concept of nitrogen balance, the ability of the body to retain nitrogen. In essence, nitrogen balance is protein balance. In a positive nitrogen balance, the body is retaining protein to adequately support growth and development, whereas in negative nitrogen balance, the body is losing protein, with possible impairment in growth and development. The quality of the protein in foods we eat may affect nitrogen balance. In general, those foods that contain an adequate content of all 9 essential amino acids to support both life and growth are known as complete proteins or quality proteins, and will have a high PDCAAS score, while those that have a deficiency of one or more essential amino acids and are unable to support life or growth are called incomplete proteins or low quality proteins and have a lower score. Relative to human requirements, an essential amino acid that is in limited supply in a particular food is labeled a limiting amino acid. Plant proteins can provide you with all the protein and amino acids you need for optimal growth and development. However, proteins usually exist in smaller concentrations in plant food. For example, 2 ounces of fish contains about 14 grams of protein, while 2 ounces of cooked macaroni have only 2 grams. 2 ounces of beans, which are generally regarded to be good sources of protein, have only 5 grams. In addition, most plant proteins have insufficient amounts of one or more of the essential amino acids, a limiting amino acid. Grain products are usually deficient in lysine, whereas legumes are low in methionine. An exception to the generality is the protein isolated from soybeans, which when processed properly is comparable to animal protein. As noted in Chapter 2, vegetarians who eat plant foods and proper combinations over the course of the day will receive a balanced supply of amino acids. Some populations receive most of their protein from plant sources. So what are some common foods that are good sources of protein? Animal foods in the milk and meat groups generally have substantial grams amounts of high quality protein. 1 glass of milk or its equivalent contains about 7 to 8 grams of protein, as does 1 ounce of meat, fish, or poultry. 1 egg contains 6 grams of high quality protein, as does 1 serving of egg beaters, but the latter has half the calories and no fat or cholesterol. Now, plant foods and supplements such as legumes and dry beans, black garbanzo, great northern, kidney, lima, navy, pinto, and soybeans, lentils, and peas, such as black-eyed and split, are relatively good sources of protein. Legumes also are high in carbohydrate and for this reason are currently classified as a starch food exchange. However, because of their relatively high protein content, legumes may be included within the meat and meat substitutes exchange list. 1/2 cup contains about 7 to 9 grams of protein. Nuts contain fair amounts of protein but are high in fat. Fruits, vegetables, and grain products all have some protein, but the content varies. Generally speaking, the protein content is low, ranging from less than 1 gram to about 3 grams of protein per serving, although some products may contain more, such as protein-enriched pasta. Some sports drinks and sports bars contain significant amounts of protein. Protein supplements targeted to strength-trained individuals may contain substantial amounts of protein, but may also be expensive. Present common foods in each of the several food groups with the number of grams of protein in each. Notice the effect combination type foods have on protein and content. For example, macaroni and cheese versus plain macaroni. Most food labels today list the grams of protein per serving. For plant foods commonly eaten in a vegan diet, review Table 210 in Chapter 2. Foods high in protein include meats, milk, cheese, eggs, and plants such as wheat and legumes. Some sports bars are also rich in protein. And this is just a chart demonstrating the protein content in some common foods. Again, look at the macaroni and cheese versus macaroni and the number of protein. Same amount, but you can see the difference in protein. So how much protein do I need? Humans actually do not need protein per se, but rather an adequate amount of nitrogen and essential amino acids. However, because all 9 essential amino acids and almost all dietary nitrogen are derived from dietary protein, it serves as the basis of our daily requirements. Billsborough and Mann noted that 3 ways of defining protein intake are absolute intake in grams per day, relative intake based on grams per unit body weight, the basis of the RDA, and as percentage of daily energy intake, the basis of the AMDR. In the United States, the recommended dietary intake of protein is based upon the RDA. The amount of protein necessary in the diet varies in different stages of the life cycle, as may be noted in the Dietary References Intake table for macronutrients in the front and side cover. During the early years of life, children manufacture protein tissue during rapid growth stages with the rate of growth and thus the protein needs varying from infancy through late adolescence. And young adulthood, the protein requirement stabilizes. Throughout the life cycle, however, the protein requirement established in the RDA is based upon the body weight of the individual. As a person passes from infancy to adulthood, the protein RDA per unit body weight decreases, but the absolute amount of protein needed by the body as a whole actually increases because of increases in body weight. Table 6.3 presents the amount of protein needed per kilogram or per pound of body weight for different age groups. A variety of scientific techniques have been used over the years to determine human protein needs, and more recent research has reaffirmed these estimates for adults and children. The values for the first year of life are AI, while the remainder are RDA. The values in this table are dependent upon adequate daily energy intake, or calories, because a low energy diet will increase protein needs. To calculate your requirement, simply determine your body weight in kilograms or pounds and multiply that by the appropriate figure for your age group. Recall that 1 kilogram is equal to 2.2 pounds. As an example, compute the protein requirement for a 154 pound or 70 kilogram average 23-year-old male. And you see they would use typically 0.36 grams of protein per pound times pounds. So 55.4 or 56 grams of protein per day. If we, on a protein-free diet, the average individual loses approximately 0.34 grams of protein per kilogram per day, which could be replaced by a similar amount of high-quality egg protein. However, allowances are made in the RDA for the fact that individual protein needs vary, that the biological quality of all dietary protein is not as good as egg protein, and that the efficiency of its utilization decreases at high dietary protein intake levels. Hence, the RDA is adjusted upward to account for these factors. The RDA for protein, as noted, is based upon body weight of the individual at different ages. If you took the recommended energy intake in calories for each group, say 2,500 calories for the average adult male, and calculated the percentage of this value that the RDA for protein supplies, the values approximate 10% for each age group. The National Academy of Sciences indicated that the AMDR should not be set below levels for the RDA for protein, which is about 10% of the energy. Mathematically, 56 grams of protein at 4 calories per gram total 224 calories, which is about 9% of 2,500 calories, or near the lower limit of the AMDR. As noted in previous chapters, the acceptable macronutrient distribution ranges, or AMDR, for individuals have been set based on evidence from interventional trials with support of epidemiological evidence to suggest a role in the prevention of increased risk of chronic disease based on ensuring sufficient intakes of essential nutrients. The AMDR for protein is 10 to 35% of energy for adults and 5 to 20 and 10 to 30% for young and older children, respectively. The health implications of the AMDR will be discussed later in this chapter. It is important to note, as Millward indicated in a review, that protein needs are determined by overall food energy intake. If energy intake is inadequate, as may be the case in those on a weight loss diet or the elderly, dietary protein may be used for energy instead of its core purpose of building tissue. Thus, some individuals may need more or higher quality protein because their energy intake may be low. In particular, some exercise scientists recommend adequate protein for the elderly as a means to prevent sarcopenia, loss of muscle mass, and osteoporosis, loss of bone mass. So how much of the amino acids do I need? The Academy also established RDA for the 9 essential amino acids. The amounts for adults age 19 or over are found in Table 6.4. Slightly larger amounts are recommended for children and adolescents. For the average adult, about 25% of the total protein requirement should consist of the essential amino acids. This amounts to about 14 to 15 grams. Phenylalanine is an essential amino acid, whereas tyrosine is normally listed as a non-essential amino acid. The two are of similar chemical structure, so that when substantial quantities of tyrosine are contained in the diet, the need for phenylalanine will decrease somewhat. The same holds true for the essential sulfur-containing amino acid methionine and its chemically related counterpart cysteine. Individuals who obtain the RDA for protein should have no problem obtaining these recommended values. So what are some dietary guidelines to ensure adequate protein intake? To answer one sentence, eat a wide variety of animal and plant foods. The high-quality, complete proteins are obtained primarily from animal foods. Meat, fish, eggs, poultry, milk, and cheese contain the type and amount of the essential amino acids necessary for maintaining life and promoting growth and development. They are high nutrient density foods, particularly if fat content is low to moderate. Because animal protein is of high quality, you do not need as much of it to satisfy your RDA. For example, for a male who needs about 56 grams of protein per day, only 45 grams are needed if it is animal protein. 1 glass of milk with 8 grams of protein will provide 20% of his protein RDA. 2 glasses of milk, 1 egg, and 3 ounces of lean meat, fish, or poultry will provide 100% of his RDA. In addition, a substantial portion of daily vitamin and mineral needs will be also supplied in these foods. As noted in Chapter 5, selection of low-fat foods will enhance the nutrient density by reducing calories. Currently, adults in the United States only consume 3.5 ounces of fish per week. There is moderate evidence that consumption of seafood is associated with reduced risk of heart disease. Therefore, in the 2010 Dietary Guidelines for Americans, there is a quantitative recommendation for seafood intake of 8 or more ounces per week for the variety. You can also go to choosemyplate.gov, click on food groups, then protein food groups to learn more about what foods are healthy choices for each of the food groups. The food gallery links may also help in determining serving sizes from the choosemyplate.gov main page. Select 10 tips. Here you will find easy to follow protein tips or easy to follow tips for consumers and professionals in a convenient format, including with protein foods. Variety is key. Plant foods also may provide good sources of protein. Grain products such as wheat, rice, and corn, as well as soybeans, peas, beans, and nuts, have a substantial protein content. However, most plant foods contain incomplete proteins because they lack a sufficient quantity of some essential amino acids. For this reason, the protein RDA for the adult male is 65 grams per day, when plant proteins are the primary source. However, Craig and Mangels into the position stand on vegetarian diets by the American Dietetic Association state that if certain plant foods are eaten over the course of a day, such as grains and legumes, they may supply all the essential amino acids necessary for human nutrition and be as complete as protein as animal protein. Some research has suggested that if the daily dietary protein is obtained through a mixture of animal and plant foods in a ratio of 30 to 70, that is 30% of the protein from animal foods and 70% from plant foods, the protein quality would be similar to the use of animal foods alone. Mixing animal and plant foods in the same meal is common and is healthful and nutritious. Animal foods provide excellent sources of essential minerals such as iron, zinc, and calcium, while plant foods provide carbohydrates, dietary fiber, and various phytochemicals. So some key concepts: protein contains nitrogen, which is an essential element to the formation of 20 different amino acids, the building blocks of all body cells. All 20 amino acids are necessary for protein formation in the body. Essential or indispensable amino acids cannot be adequately synthesized in the body and thus must be attained through the dietary protein, whereas non-essential or dispensable amino acids may be synthesized in the body. Conditionally, indispensable amino acids may be synthesized from other amino acids under normal conditions, but their synthesis may be limited under certain conditions when insufficient amounts of their precursors are available. The RDA for protein is based upon the body weight of the individual, and the amount needed per unit body weight is greater during childhood and adolescence than during adulthood. The adult RDA is 8 grams of protein per kilogram of body weight, or 0.36 grams per pound of body weight. The acceptable macronutrient distribution range, or AMDR, for protein indicates that dietary intake should be no less than 10% and no greater than 35% of daily energy needs. The human body needs a balanced mixture of essential amino acids, and although animal protein provides all of the essential amino acids in the proper blend, a combination of certain plant proteins such as grains and legumes will satisfy this dietary requirement. Although animal foods in the meat and milk groups have high protein content, they may also be high in fat. Increasing the proportion of dietary protein intake from plant sources is recommended. Combining animal and plant proteins in one meal, such as milk and cereal, or stir-fry vegetables and meat, will increase the protein quality of the meal. Thank you for joining me today. We will continue our discussion on proteins in part 2 in just a bit. Have a good day.